Okay, so we are going to continue where we stopped the class yesterday, that were about discrete Fourier transforms. And what I will going to explain now, just next, is going to be related to the tutorial, to the exercise that you have to do this afternoon. So pay attention, because you will need this information. So, either today and also in lecture courses, I'm going to randomly denominate t, like the total observation time, the duration of the time. Sometimes you will see that I write t coherent, meaning the coherent integration time. And sometimes, not always, you will see me writing t ops, that is the total time of the observation. Not necessarily these are all the same. So basically, I use a sampling duration that is the total coherent time divided by this number of points. And I'm going to use, as discrete Fourier transform, I'm going to be used the following convention. And what I will be writing next is only valid following the normalization factors that I will be introducing. So let me define the Fourier transform with this delta t included here. So this normalization factor here is important, and as the return, k can take the values between 0 and n minus 1, and this corresponds to the Fourier frequencies, as I was talking yesterday, of k times the discretization in the Fourier domain. That is the full duration of this interval. The data, I said, or my assumption, is that it's a combination, is a sum of noise plus a signal. And I'm going to work under the assumptions that the noise is an stochastic process that it is stationary, that is Gaussian, and with zero mean. In this case, the one-sided power spectral density can be computed or can be defined in this way, where this represents an ensemble average. We have not yet shown you sensitivity curves of the interferometer detectors. You will see them in the afternoon, but basically it's clearly non-white. It changes several orders of magnitude in the corresponding frequencies. Therefore, it's quite important for many searches to define a quantity that we call the normalized power. And I can define the normalized power at a given frequency in this way. So basically, this will be the way to compute how much power you have on the expected value of noise by converting basically your output into as if it would be white noise. So then basically there will be not much difference at different frequencies. This quantity here, it can be approximated or it can be related to this one-sided power spectral density. This is not exact, this is just an approximation. And then this quantity then is T coherent divided by 2 Sn of Fk. So basically, the normalized power can be approximated to 2 times xk. So we can approximate it by this quantity. 2 times this power, we can rewrite it as a sum of 2 quantities where zeta1 is square root of 2, the real part of the Fourier transform of x divided by this related to the noise, and z2 is the imaginary part k square. And basically, in the Fourier domain, the output of the detector is just going to be the Fourier transforms of the data and the noise, of the signal and the noise. So this Z1 and this Z2, if I substitute this by these approximations here, this I could rewrite like square root of 2, the real part of x divided by the square root t coherent over 2 Sn of Fk. That is going to be then 2, the real part of x t coherent Sn of F. And if I do the same with Z2, I'm going to get that Z2 is 2 times imaginary part of the Fourier transform of x t coherent Sn of F. I can also assume that both the real part of the noise and the imaginary part of the noise are also independent random variables with equal variance. And then it's easy to show that their variance is equals to this quantity here. So if I take that the noise is Gaussian, then it just follows that both these two random variables, Z1 and Z2 are also normally distributed and have a unit variance. Okay. They will have then Z1 and Z2 unit variance, but they will not have is a zero mean unless we don't have any signal in there. So, starting from that point, then it follows that 2 rho k should be distributed according to a chi-square distribution with 2 degrees of freedom, with a non-centrality parameter that I can compute it like the mean Z1 squared plus the mean Z2 squared, and this non-centrality parameter equals to 4 times h fk square the coherent Sn of fk. So basically, the distribution of rho k given a certain non-centrality parameter is 2 the chi-square of 2 rho k with 2 degrees of freedom and this non-centrality parameter that is given by the expression exponent minus rho k minus lambda k divided by 2, and this is the modified Bessel function of 0 order of square root of 2 lambda rho k. So from here, what is important is that when I have no signal in the data, my non-centrality parameter is going to be 0, and basically this distribution is simply the exponential distribution. The mean of rho k is 1 plus lambda k divided by 2. The variance rho k is 1 plus lambda k. So the exercise that is going to be given to you this afternoon is going to be that the tutors are going to provide an analytical expression of the one-sided power spectral density, and you will have to produce some coherent segment, let's say 5 minutes, of data that have these properties. And after you have been able to produce this time segment of data, you will have to check with the method I was describing yesterday, with the Welch method, that when you estimate the power spectral density from the noise itself, you recover the analytical expression. Of course, if you just plot the periodogram, it's going to be very noisy because the noise will be the error as large as the measured, but then applying the Welsh method, the error bar will be reduced. How this exercise can be done? Basically, I've put all the information in this whiteboard here. Then you have to remember the properties. And I would like you to produce, maybe this is going to be a horrible function, and if you're interested that you produce data, let's say, containing information until 2 kilohertz, that's going to force you a certain sampling rate of at least 4 kilohertz. Of course, this is not going to be as simple because this diverges, so there is going to be some cutting that you can set the value of this function to 0 outside of the range. So instead of infinite, you can set it to 0. And basically, I ask you to produce this data. So data with no signal. So basically, what I'm saying is that the Fourier transform of H is 0 everywhere, meaning that I have the non-centrality parameter everywhere, and that means that simply these two quantities that I've defined there, Z1 and Z2, are going to be Gaussian noise with a 0 mean and variance of 1. Okay, so that means that the real part of the noise is going to be Z1, 1 divided by 2, T coherent Sn of Fk, and the imaginary part of Nk is going to be Z2, 1/2 T coherent Sn of Fk. So basically, this is the exercise. It's like, oh, we are going to mention that we want to produce data of a certain duration. Given the duration, you know which is going to be your frequency resolution, because your frequency resolution was 1 over this total observation time. Then you know which is the discretization you have in here. You know which are all the values of these Fourier frequencies. This is an analytical expression, quite horrible, that it will be given to you. And then for all the different values of frequencies, you just have to produce the real part and the imaginary part. For the negative frequencies, they are just going to be complex conjugate. Then you just have to be careful about the number of points you have, if you are producing an odd or an even number of points. And then the properties of Fourier transforms, because basically it assumes that in both in time domain or in Fourier domain, the things are periodically. So it doesn't matter if you produce data from here to here and the negative ones, or if you produce double the amount of range. So these are the basics of the exercises for this afternoon. And given that, let me start then the new topic that are going to be tools and statistics. Of course, there is more information I could include here. That is, when we are doing Fourier transforms or when we're dealing with data or we are filtering, we don't work just with a rectangular window, with a start and with a stop. We usually work with other kinds of windows that have different properties. And the properties that are going to have is that they are going to prevent, let's say, some leakage. But I think I'll leave that to the tutorials. Where were the tutors? I don't see them. Okay, so windows is included? Okay, so the windows are set for the class. So let's change topic now. and I will start talking about tools, statistics, and probability. So, some people think that people working on methods for data analysis, that this is like kitchen cooking recipes. But recipes don't only work as you expect. You can have surprises. So you better understand what's the problem. I see some people saying yes. So I guess you work on data analysis? Okay. So you have to understand the problem, the properties of it, the properties of the tools you are going to use. So the problem that we are dealing with faint sources. We are going to handle very large data sets. We want to avoid unnecessary assumptions. Of course, we will also like to have tools able to estimate parameters and test models. Or we also want to have tools able to do diagnostic, to find diagnostic system errors and so on. I'm going to work with data that also have some noise. So whatever statement I make on it is going to be assigned some kind of probability. And now comes the problem. There are different interpretations of what probability means. I'm not going to cover all the possible interpretations of the definition of probability. I just will focus on two. One, as a measure of our degree of belief in a statement. And another one as a measure of limiting relative frequency of outcome of a set of identical experiments. So my first interpretation of probability is what is called the Bayesian approach. And the second one is the frequentist approach. And it's hard to say what is better and what is worse. I guess it depends on the problem. So I'm not a religious fanatic on that. And actually depends on the problem that I'm solving. I put the hat of Bayesian, and the next day I might put my hat of frequentists. I'm more frequentist, but now both have issues because the definition of degree of belief is hard to understand, or this limiting relative frequency, okay, of identical experiments. That's also interesting. Luckily, whatever probability framework you prefer to work, the algebraic probability is always the same. So at least algebra, I can just work of the algebra of Bayesian probability. This is basically, you all agree that the probability if something is true, we say it's 1. The probability of false is 0. And the probability, if not sure, it's something between 0 and 1. Then there is the sum rule, that the probability of certain statement plus the probability of the negation of this statement is always 1. And if I have two statements, x and y, then using the product rule, I can define the joint probability of x and y as the probability of y times the probability of x given that y is true. So this means probability of x given y is true. Of course, the joint probability of x and y, as I just said, I can just write that the probability of y is the probability of x given y is true, or the probability of y and x, probability of x, probability of y given x is true. This is the same. So since this is the joint probability, these two quantities are the same. I can just equalize the right-hand side of both equations. So if I say this is equal to this, then what I get is that this is the same. Can people see it, or this is already making shadow? And from here, I can just isolate one part. I just can rewrite like this. So basically, what I just written was the bias theorem. Can rewrite the bias theorem a bit nicer. And basically, I can write the probability of a certain model given my data. Then this is equal to the probability of the data given a model times the probability of the model probability of the data. This is known as the posterior distribution. This is the likelihood. This is the prior. And this is the evidence. And these are the things that we can compute for the data itself. And this is what we would like to compute. I can talk about marginalized probabilities. And for example, if X and Y are propositions that can take on values drawn from different sets, then the probability of a certain value, I can just write it basically in this way. Because this basically I just multiply by a 1. Then I can move this inside the summation. And these two things here is nothing else than the joint probability of these two quantities. So basically, the Y is what we can call the nuisance parameter and if instead of working in a discrete case, I go into the continuous case, basically I can generalize this expression and get that the probability of X, this can be obtained by what we call marginalizing over the parameter Y. So basically this gives me the probability of X when I don't care about the probability of Y. Excellent. So if I do the work of computing the probability of the model given the data, but this model depends on many parameters, but basically I'm just interested on one parameter, for example, the amplitude of the gravitational waves, what I could be doing is to marginalize through all the other unknown parameters. So when I have already done this, then I can worry, or I can already compute many things, because I can work on Bayesian parameter estimation. So basically, I could have distributions. I could have the posterior distribution of any parameter of my model given the data versus this parameter. This could have whatever shape. And from here, I can extract a lot of information. I could extract the most probable value of this distribution. I could compute the mean, or I could compute things like confidence intervals. So the interval between two values of this parameter related to whatever confidence interval we want to set. So if we would like to set a confidence interval for a given parameter, let's say of 95%, what we will have to find are which are the values of these two parameters that the integral of this curve and between these two values gives you this 95%. Of course, there is not a unique way to define this confidence interval, because I can easily imagine that if I move this slightly a bit here, maybe I have to move this a bit more there, and I can also cover this 95%. So typically one finds is that either you want it centered to something, or you define the confidence interval to be the shortest. So here you have seen something very clean. Whatever is the parameter of interest, possibly the amplitude of the signal, that will tell me amplitude of the signal is also between these two parameters. Of course, I could have many other posterior probability distributions, like whatever thing in which I don't have a clear maximum, and then maybe I'm talking about the amplitude of the signal. So then I don't have not detected the signal. And if I have not detected the signal, instead of talking about confidence intervals, I might end up talking about upper limits. And then this is going to be corresponding to the value of H0, such as below it, it has the confidence level of the upper limit you want. So if you want 95% upper limit, then you will extract from this distribution, which is the value of H0. And depends how broad this distribution is, you will claim that you have a detection, or even this could be doing things, if you have a maximum clearly separated enough from 0. So this was the Bayesian approach. The summation.
Why is the summation of the probability for y when x is true?
Because you are summing from all the possible values of y. So if y can take any value from this distribution, if you are summing from all the possible of them, the sum of all of them is going to be 1. Okay? So because it's either this, or this, or this, or this, or this. It's like the integral of all the distribution probability is normalized to 1. Now let's go for the other approach, the frequentist approach. Now, in the frequentist approach, or orthodox statistics, basically only random variables can have frequentist probabilities. So basically, the measurement of the mass is a random variable, but the mass itself not. So as a frequentist, if I have here a scale, it can only tell me about what is the probability that the scale gives a certain number when I step on it, not about how massive I am. Okay? Because the one that tells me which is the probability that my mass is whatever and growing is the Bayesian approach, not the frequentist approach. So basically, in the frequentist approach, we are going to have a parameter in the model, and we are going to have what I put with these hats on top, the estimator for this parameter. And this is why yesterday I was already putting the hat on the estimator and the power spectral density. So basically, here what we have to do is to construct an statistics that is a function of the data. Now, a good estimator is going to have a probability density distribution that is going to depend heavily on the value of A. So a good one is going to have a certain distribution, and if it's a good one, we want it that is heavily peak, sharply peak if possible, at the value or close to the value of A. And then this could be here, what is the measured value of my estimator. There is one estimator is the maximum likelihood and one way to construct this maximum likelihood is that given certain data, this I could construct like the probability of data 1, I, probability data 2, I, etc. if the data points are all independent. So I can construct this probability as the product of all the probabilities. So then I construct the likelihood as a function of A, and then we get this value here as the value of A that maximizes L of A. And then one can plot And now we can plot the probability of the maximum likelihood given A, maximum likelihood given the certain value L, and this is going to have a certain shape and is going to have a certain width. Okay, we might be interested in then finding which is this width, such that the probability of A minus the width, maximum likelihood, A plus the width, to be, for example, 95%. And basically what this is going to mean is that 0.95 is the relative frequency that the parameter A lies in the region maximum likelihood plus minus taka is true over repeated experiments. So basically, if this is my value of A, then it could be that I repeat the experiment and gives me sometimes this. So it tells me, no, I did not grab it in the proper interval. Then say another experiment, it repeats this, and then, oh yes, now it got through. Yes, it's inside this interval. Yes, no. So if I do different experiments, this interval basically tells me that the relative frequency that the real value has ended up being in this interval. By no means you can try to interpret this saying that the value that we are searching for, so this by no way is I maximum likelihood plus minus tuku with the 95% confidence. So what I'm making here the point is that Bayesian confidence intervals and frequencies confidence intervals do not mean the same things, and therefore they don't need to be the same. Now, following the frequentist approach, I can talk about frequentist hypothesis testing. So we would like to test a certain hypothesis that I call H1. For example, that my data has a gravitational wave signal. And the way we do it is that we consider another hypothesis, H0, in such a way that if H0 is true, then it will deny H1. And then what I'm going to do is to argue against H0. So what I have to do is to come out with a certain test. So I can have T, that is my test, or it is my statistics. And what I have to deduce or construct is the probability distribution of the results of these tests, given that the null hypothesis is true. And from here, what I have to do is to put somehow a threshold on the values of the outcome. For example, I can fix a certain threshold. And what I would say is that when I do a test, the value that I measure of the tests, if it fails in this region, if it's higher than T asterisk, what I will be doing is that I will reject at 0. And if it fails below, I will accept H0. So this is quite funny, because basically I just want to search if there is a signal in the data, and I'm just arguing if the outcome is consistent or not with noise. And I'm not saying anything at all in this way that I proceed regarding what am I searching. So this sounds a bit crazy. So if I know, for example, what I'm searching, I can not only here draw the probability of the outcome of the test given my null hypothesis, I can also characterize the probability of the outcome of my test given the signal hypothesis. And then this was my threshold. So basically, I can just write with these drawings of certain probability distributions, but it's basically like whatever test you design, if this is all possible outcomes of these tests, what you will have to do is going to be divide all the possible outcomes, and then you will say, okay, if it lies here, null hypothesis. If it lies here, non-null hypothesis, there is signal present, signal absent. I think it's much more easy to understand in this way, because in this way, there are many errors that I can now characterize. I mean, because it could be that actually there is just noise in my data, but my outcome might have fallen somewhere here. So there is a probability this probability here is the so-called false alarm probability, and therefore this is false alarm. Alpha, given a certain threshold, then is the integral from this threshold to infinity of the probability distribution of the test given the null hypothesis. And the other error I might be doing is that maybe my outcome is below this threshold. Therefore, I accept the null hypothesis, but actually, this is compatible with the signal. So this is the other error I can do, and this area here, is the false dismissal probability. So the false dismissal then is the integral of the probability of t given h1 being true dt. So what we would like to come is with a test that actually minimizes these two errors, the false alarm and the false dismissal. Okay, so according to the Neyman-Pearson lemma, the optimal test is the likelihood ratio. And this likelihood ratio of the data given a certain signal is the ratio of the probability of x given the signal divided by the probability of x given that I have no signal. In the case of Gaussian noise, basically one can find that the log of the likelihood is the well-known match filtering amplitude. And these symbols that you see here were the scalar product that I was introducing yesterday. So basically, the way it goes, if I say that x of t, that is the data, if this is a sum of the noise plus a certain signal that depends on a number of parameters, what we have for Gaussian noise, what we have is that the probability of the noise is basically proportional to E scalar product of the noise by the noise divided by 2. And the probability of the data containing the signal is this x minus h lambda, x minus h lambda divided by 2. Yes?
Ideally, it would mean that those two curves shouldn't be intersecting.
What is going to happen is that it all depends on the signal. So if your signal has a very low amplitude, the distribution are going to be very close to each other. If you are working with stronger amplitudes of the signal, this distribution become more and more far apart. And if it's very strong, this is very far apart. How far apart is the distribution of the noise versus the distribution of the signal is going to depend on the kind of test you decide to do. So basically what I'm telling is that the recipe for when you know exactly what you are looking for, the test, the statistics that are going to separate more these two distributions, and that's being match filtering. If you do different statistics, that is usually what I will talk, I use other things. Yes, there's going to happen things like that, but they don't get separated enough. And therefore, for a certain false alarm probability, since the two distributions will not be that separated, you will only be able to detect stronger signals. And the optimal test is the one that allows you to find the weakest signals. Did I answer your question? Yes, the likelihood is the best test when you know what you are searching for. This is the hypothesis that you have a signal. And here, what I'm doing is that I'm saying that n is x minus h. If this is Gaussian, this is true. And if I have a signal present, I just substitute n by x minus h. This, now you can easily derive that this I can rewrite it like n a 2 minus 1/2 of x with x minus 1/2 h with h plus x and h. Therefore, my likelihood of x and h is the probability of x given h, the probability of x when I have no signal. In this case, when my data is just noise, this is, I can just rewrite it like x with x divided by 2, and this was x divided by 2 minus 1/2 lambda plus x lambda. So this and this gets cancelled, and the logarithm lambda x h is just what I have written before, minus 1/2 h lambda. There are many more things I can do. I know that this is the optimal, but I can also maximize the likelihood, let's say, with respect to the amplitude. So if my signal, if I could rewrite it like a given amplitude times another one, so this is just to scale, then the log of the likelihood This is going to write it like x H0 minus 1/2 A HA A HA. That means this is A times H A minus 1/2 A squared. And now if I want to find the maximum, just what I have to do is to derive with respect to A. That is going to give me just these quantities here. I just make it equal to 0. And therefore I can deduce the value of the maximum likelihood of this parameter that is given by this quantity. Okay. So then what I can do is that now I can substitute the value of A in here before deriving. So I can put the value of the maximum likelihood here. And then what I will get is that this is x HA x HA minus 1/2 x HA squared times HA. Excellent. One of these goes with one of these. And this is nothing else than 1/2 x HA squared HA. Or if you prefer, I just can rewrite it that this is 1/2 of HA's normalized. Okay. What I want now is that this has been a way to deduce this optimal filter following this Newman-Pearson lemma. But let's try to deduce another way of deducing these optimal filters. So I want to find the optimal filter. So I have my data, that is noise plus a possible signal that depends on parameters as a function of time. I am going to make the assumption that my noise is 0 mean. And if my noise is 0 mean, you should notice one property is that the ensemble average of A of the scalar product given A and B any 2 times series, the ensemble average of the scalar product of A times the noise and B with the noise equals this quantity here. So given my data, I'm going to filter the data. So I'm going to denote the filtered output of the data with this H hat. For example, this H hat I could construct applying these linear filters. That is just I am filtering my data with a certain filter. And basically what I want to find is the choice of this best filter, this function k, that is going to amplify the value of the x hat. Of course, if my data is the sum of noise plus a certain signal, one way to amplify this integral would be, or the first thing that could cross my mind, that is not going to be the optimal choice, but my first choice is going to be, if I would get that this filter is exactly the signal that I'm looking for, clearly this is going to amplify the value of this integral. Now the question is like, is this the best choice? No, not yet. So what is going to be the best choice? The best choice, or the optimal filter, is going to be the function that maximizes what we call the signal to noise ratio. And the signal to noise ratio, basically independent of what you do, is the ratio between the expected value of the filtered output x when the signal is present divided by the root mean square of the filtered output when the signal is absent. By doing these kinds of operations, basically I can rewrite that the signal to noise ratio, even going to Fourier domain, is going to be the integral from minus infinity to infinity df h lambda f kf df 1/2 SNF. Here I have jumped several steps to get into this. And this can be written in a more compact way. The scalar product of this quantity that I will define next where this u is 1/2 SNF, the Fourier transform of the filter. So what we want is to choose a u, a k, therefore a u, that maximizes this quantity here. So this is the scalar product of these two quantities divided by, beautiful thing, normalize. So if I imagine things like vectors, if I have the scalar product of two vectors, when is the scalar product of two vectors maximized? Exactly, when they are parallel, when they are proportional to each other. So the optimal filter is going to be, my optimal is when U is parallel to H, therefore, when this Fourier transfer of the filter is proportional to the Fourier transfer of the data with this ratio here. And in this case, if now I substitute it here, what I'm getting is that Sn square is nothing else than 4 times, or I can rewrite it in this way, so this is the optimal SNR, the maximum SNR you can get. And this also tells us, this is also telling us that the optimal filter or my optimal test, my optimal statistics, what operation should I be doing with the data? So my optimal search statistics basically what it tells me is that the operation I should be doing is this operation. In which here the templates have been normalized with respect to the noise, and this is called the Wiener filter. And of course, Sn is the power spectral density of the noise. Okay. So basically, what I have to do all the time with my data is to compute scalar products of the data with my expected signal. Let's compute what is the signal to noise ratio in this case. So the signal to noise ratio, let me convert it into my scalar products. I said is the expected value of the test, expected value of the test. So I get my data. I just multiply, I do the scalar product with the signal that I expect is in there, divided by the root mean square of n h lambda n h lambda. Okay, so this is n h lambda plus h lambda H lambda. And here I can apply the property that I introduced before. If this is a zero mean, this is going to give me H lambda, H lambda. The numerator, I can write this is the mean of the noise plus the mean if I say that the noise was zero mean, then this quantity is here, it's zero. This is completely deterministic. Therefore, I'm getting that this is H lambda, square root, H lambda, H lambda. So therefore, if I do much filtering, the optimal filter, the maximum SNR I can get is this quantity here. Now, the problem is that I not always know exactly what am I searching. So my data maybe is the sum of a noise plus a certain signal that depends on a certain parameters. But I'm using another signal, a different signal, a template to search. In such case, this signal to noise ratio, what I'm going to get is XH template, and here and H template and H template. So this was N plus the signal, the template, template. Again, this is then H lambda, H template plus N H template H template, H template. I hope you can follow. This is again this 0. So this is H lambda, H template, H template, H template. So this is nothing else than the scalar product of H lambda, scalar product, H template normalized. So in short, if you know what you are searching for, the best statistic is going to be to do your scalar product of the data with your normalized templates. Of course, you recover the best amplitude of the SNR when exactly this is exactly the signal that was in the data. And this is called match filtering. Things are easier in my case. I'm looking for almost monochromatic signal most of the cases. Could not be true for young neutron stars that Keith was mentioning. So typically for these long-lasting, boring, old neutron stars that the frequency does not change so much, what happened is that my power spectral density in a very narrow band is going to be very similar. So I could basically consider that my noise in the band of interest to be white. If my noise is basically going to be white, I can take this Sn out of the integral that I have to do. And then, if I'm just looking for a monochromatic signal, what it's telling me is that for a monochromatic signal in white noise, my optimal filter is simply a Fourier transform. Let me introduce some more things. Now let's go to the problem of the templates. So let's assume that I have two different templates, two of these waveforms. And my gravitational waves from continuous signals, they are going to depend on a number of parameters. I will come back to that tomorrow, basically, or tomorrow, yes. So my parameter space would depend on the frequency, on frequency derivatives, possibly in the sky locations, possibly in many other parameters. That means if I want to recover the best signal-to-noise ratio, I would have to search for all possible values of all the parameters in a certain parameter space. Of course, I cannot do that with an infinite resolution. So in my parameter space, I will have to put a grid. Of course, I can avoid the grid. I could do gridless methods. But if I want to refine, I have to set quite a refined grid in an n-dimensional parameter space, and I have to know how far away I have to place these templates one of each other. And this is my choice of how far away I want to place them. Basically, is going to depend in which is the loss of SNR that I let. Okay, usually we choose a grid on SNR such that the loss is just of 3%. Why? Because my signal, the amplitude of the signal, whatever emission model I consider, and don't care if it's continuous or is a CBC signal and so on, the signal amplitude is inverse proportional to the distance. So if with one optimal search, I was able to have a certain reach, now because I put a certain grid, if I lose a 3% in SNR, means I'm losing a 3% on my distance. And a loss of a 3% in the distance, if I now want to compute which is the loss in volume, it's going to scale as r to the cube. And then this 3% loss basically is going to imply a 10% loss in volume. Let me define another quantity that is called the match. Well, there are many ways to define the match between two templates. So a match between two templates, I can just define like the scalar product normalized. So basically, this is going to give me, this is going to be a quantity ignoring the sign between 0 and 1. And if it's close to 1, it means that these two templates are the same, modulus amplitude. But it tells me how much they differ. And another quantity that is very important are the so-called fitting factors. That is, the fitting factor for a given template bank is the maximization of this match between the signal and all the possible templates. In order to place the templates in the grid, I can then define a distance. So I can define the distance of two templates that have different parameters, like 1 minus the square root of 1 minus the match of these two templates. So the distance square between, let's say, a certain point in parameter space and another point in parameter space slightly shift, basically is 1 minus the match of these templates that depends on lambda, the template of the other one that is slightly shift. And if the distance, if the separations is not too much, then I can introduce here the metric of the parameter space. And this metric tensor that depends, of course, in the point in parameter space can be computed like the second derivatives of this match. And this is basically the best way to set a template bank is going to be really computing the metric for the problem in question and then placing a grid. I think it's 1 o'clock. Then I stop then the class here if there are questions. So from tomorrow on, I will already focus on neutron stars and gravitational waves, because as you realize, the first 2 lectures can be very, very generic, and they could not have applied to many other problems.
So do we have any questions before we conclude the session? Okay, so if not, let's thank Alicia.
Hello, I had a question, if that's okay.
Sure.
Yeah. So when we were taking the initial assumptions, we assumed a linearized way of dealing with this, and also we did a Gaussian approximation for our signal. What happens if we don't take that assumption? Like if we look at the nonlinear regime and more into the non-Gaussianity, if we do that, although it's very small, I believe.
I think I will be covering this issue basically on Thursday, because your question is completely fair, and that's the real day-to-day problem, that our data is not Gaussian and our data is not stationary. So just with the integral that I have to do match filtering, there was this estimation of Sn, and Sn, as I will explain then tomorrow, in order to search for continuous wave signal, I will have to integrate with very long stretches of data. And therefore, the signal to noise is changing between day and night. So that's the first problem. And the second problem that you raise is that match filtering is the optimal filter for if we know exactly what we search for, and in the case of Gaussian noise. But our data is not Gaussian. It's full of artifacts. It's full of plenty of transient noise and also long-lasting signals, lines that I will also mention. Then, well, we can still try to apply this optimal test for Gaussian noise, but then we will have to develop other strategies, other vetoes, that will be able to discriminate if the data was real, of astrophysical origin, or if it was not, if it was because of the instrument or because of the environment. So that will be covered, all these follow-ups that we do and all the veto strategies that we do in order to discriminate and to assign a significance to the outcome that we get from the data.
Okay, got it. Thank you so much.
Ma'am, I have a question. So when I was studying this Bayesian statistics, then I came across credible intervals. So what is the difference between these credible intervals and confidence intervals?
I guess it's because I might not have used the correct word. Maybe Keith can correct me. Credible intervals are the Bayesian names, and the confidence intervals is the frequentist name. I guess it's basically the name you give, and basically proper people will use the different names to make sure to let you know if you are doing Bayesian analysis or frequentist analysis. So credible intervals, I guess, is going to be the Bayesian. When I have done the drawing, I should have put credible intervals. And when I've mentioned the frequentist approach, I should have come with confidence intervals. Hopefully I have not reversed, because I mixed them. I've mixed the notation. I just try to understand what they mean. But they don't coincide. They can be very close by. And they don't mean the same. That's the important message.
Okay, so let's thank Alicia one more time.